Moving on to chapter 13, chemical equilibrium, and I realize this is going to be a very interesting video because I might lose my voice partway through it. Hopefully I won't, but you might have to read without me speaking. Okay, first, the equilibrium condition. What is that? This is where the concentration of all reactants and products stay constant over time, but it doesn't mean that the reaction is not still occurring. In fact, the reaction is occurring. And on the molecular level, there is frantic activity, all sorts of activity, lots of activity going on. Equilibrium is not static. It's extremely dynamic. It's a dynamic situation. Okay, let's look at some pictures. How do we identify, why is this not working? We're going to have to pause. Okay, we're back on. Let's make this go away. Okay, so on the left side, over here, we have concentration versus time. And as time is increasing, we see some of the concentrations go up, NH3 is going up, whereas N2 and H2 are going down. And we've reached equilibrium when the concentrations no longer change. So right here, you should notice that the concentration suddenly flatlined. You are at equilibrium when the concentrations flatline. And just for your information, this particular reaction, NH3 is a product. You should be able to figure out the reaction just from looking at the graph. We know that NH3 is a product, and we know that N2 and H2 are decreasing, so N2 and H2 have to be reactants. And now we can just balance the reaction. So let's see, we get N2 here, and I wrote N2 twice. That's an H2. Let me fix that real quick. This is an H2, and we need 3 of those, and there's our reaction that's happening. So we've reached equilibrium right at this time when the concentrations flatline. We saw some graphs that looked a little bit like this in kinetics. And now this is kinetics over the right-hand side, reaction rates. You should recognize reaction rates. So here's our forward rate. And over here is our reverse rate. And notice there's a point where the forward and the reverse are equal. That moment, right when the forward and the reverse rate are equal, is called equilibrium. So right here, at this time, and all times forward, the system is at equilibrium. And the reaction is still going forward and reverse. We need a double arrow there. The reaction is going forward and back. That is a really ugly arrow. Yeah, that's a little bit better. So that reaction goes forward and back at the same time. The key is the forward rate is equal to the reverse rate. We just did this when we were looking at mechanisms. And you're going to find that the equilibrium constant is actually just your K forward, actually your K reverse over your K forward. So we're going to see that in just a moment. All right, so the equilibrium constant. What is that? Hopefully you remember this from before. So we have our equilibrium constant K. It's our products over our reactants. And we raise each product to the power of its coefficient. And that is written for you over here. No, it's not. It just should be obvious. I didn't write it down. We just raise each chemical to the concentration, to the power of its coefficient. Okay. You have a handout that I made of all of the terminology, and the terminology defines the equilibrium constant expression, which is this right here. Okay, and we should note that K is Kr over Kf, and this comes through our kinetics, from looking at kinetics. I'm not going to derive that right now, and you won't ever have to use this, but it's just an interesting little connection between kinetics and equilibrium. Okay, let's do a problem. So we have the following equilibrium concentrations for a specific reaction, and we want to calculate K for the reaction at 127 degrees Celsius. We don't ever use the temperature in these equilibrium problems. They're always given to us. You just need to know, you have to check that you're at the same temperature for solving for K as for the initial conditions, or the equilibrium conditions. Okay, so try to set this up on your own, or pause the screen. The answer is about to show up. If you have no idea how to just plug in, do products raised to their power over the reactants raised to the power of their coefficients. Okay, pause if you want to try it on your own. Here's the solution. Okay, here's another problem. You all said you like to have more practice problems, so go ahead and pause. I'm about to show the answer. Oh, notice I reversed the reaction here. That's important. Wait a second. Here we go. The reaction looks different. So we know the equilibrium concentrations, but we have a new K because we have the reaction's written differently compared to the first reaction. Okay, and so you can try it on your own. The answer is about to show up. There we go. Okay, and again, notice I reversed the reaction there. And you should notice something about these two numbers. When you reverse a reaction, something happens to the K. Do you notice that these numbers here are just the reciprocal of these numbers right here? That's because if you reverse a reaction, your products and reactants switch places. So you just take the reciprocal of the original K. I don't even have to plug in my numbers right here. I could have just done 1 over 3.8 times 10 to the 4th, and that I would have gotten that same answer. And here I have what I was just talking about. The answer for B is this reciprocal of the answer for A. If you reverse a reaction, the new equilibrium constant is just the reciprocal of the equilibrium constant from the original reaction. Okay, I've got a whole bunch of generalizations here, and I'm going to cover them up a little bit. I don't want you to see below there. There we go. Okay, some generalizations. First one is what we just talked about. I'm not going to repeat it. Another one, this is a very important one. If you multiply a reaction by a factor n, so if you double a reaction, for instance, then you're going to raise the equilibrium constant to the nth power. So if you double a reaction, K, the new K would be the old K squared. That's K prime. So double K would be K squared. The new K, K new. That's not right, K prime. If we triple a reaction, K new would be the old K cubed. If we have a reaction divided by 2, we would raise K to the 1/2 power or square root. Okay, no units on K. We don't worry about units. There's a problem later on where I'm going to put units in just so you can see how some units cancel, but you don't ever have to report units for K. All right, if K is very small, since K is products over reactants, that means if K is really small, then the products are very, very small compared to the reactants. It's important to just keep that in mind. If you see very large values of K, remember, K is products over reactants. So if K is really large, products are really large compared to reactant concentrations. All right, about pressure. Everything I've talked about so far, we've been using concentrations for those Ks. When you see a K with no subscript, we assume we're talking about K with concentration. But sometimes we can have partial pressures, and we can still write a K for those. And that K would look like this right here. So when you see the little p, that means equilibrium pressure, equilibrium constant. This little c here says concentration. If there is no subscript, we assume concentration. But if there's a subscript p, we're talking about partial pressures instead of concentrations. When you see K with no subscript, there are problems referring to KC. I've said that about 3 times now. So it sounds like that's something that's important that you should remember. Yes, you might want to put a little star here. Oh, my stars aren't working. Okay, so very important. I've said that a bunch of times. No subscript, concentrations. All right, so there is actually a relationship between Kc and Kp because we have an equation PV equals nRT. Now, N over V is concentration. So N over V, let's see, what is that going to equal? P over RT. So P is pressure. N over V is concentration. P is pressure. And from that information, you can actually derive this relationship right here. Probably going, what in the world is that delta N? Now you know delta N is the moles of gaseous products minus the moles of gaseous reactants. Let's do a problem. Find Kp for question 1a on page 1. I've given you all the pertinent information, so we're already working with this reaction in problem 1, and we want to find Kp in terms of Kc. We already know Kc. We know the temperature. We have to first calculate delta N. So delta N, moles product, is 2. I put that under the reactants, which that's a bad place. Let me do this over here. So the moles of product, gas products, we only look at the gases. If there were solids or liquids in here, we would ignore them. So 2 minus the moles of reactant gases. We have a 3 and a 1. So 2 minus 4 is negative 2. Right there, delta N is 2 minus 4, negative 2. Let me just plug into this equation. For R, we always use the gas constant in atmospheres liters per mole Kelvin, which is 0.0821 atmospheres liters per mole Kelvin. And you should pause and plug everything in here. Don't forget to use Kelvin right here. If you didn't pause, you're about to see the answer, and here it is. All right, now I told you that you don't have to use units for Ks. I did include all the units here just so that you could see the relationship and what happens. So the original Kc would have the units of per molar squared if we looked at the units, because we had molar squared over, this would give you molar to the 4th, which is molar to the negative 2. Okay, so these would be our units for Kc if we had kept them. And now molar is moles per liter. So right here, these moles per liter and this molar to the negative 2, because we also have a negative 2 over here, those cancel with each other. And the Kelvin cancels with the Kelvin. So I end up with atmospheres to the negative 2 power. And we have a Kp, pressure. Now, again, we don't worry about the pressure units, but I'm just showing you here, we do ultimately end up with the correct pressure units if we were to include the units, because Kp would be pressure squared, so you'd have atmospheres squared over atmospheres cubed times atmospheres, which is 1 over atmospheres squared, which is atmospheres to the negative 2. Okay, just showing you the consistencies with the different units. Again, you don't have to do that. I'm just trying to show you that all of these things, they do work with each other. On to heterogeneous equilibria. We talked a little bit about homogeneous versus heterogeneous for kinetics. In class, I mentioned a few things. I told you you don't have to memorize anything about it, and even in this, there's nothing to memorize. Heterogeneous just means you have more than one phase. So here we go. If a reaction involves more than one phase, the equilibrium is heterogeneous. Just like kinetics, if the reaction is more than one phase, you have heterogeneous kinetics. Only one phase would be homogeneous, and everything we've been doing so far has been homogeneous. Okay, so where this comes in is if we have a heterogeneous reaction, we ignore solids and liquids. We do not ignore aqueous substances. We have to include things that are aqueous. Those are not liquids. Those are things dissolved in water. So we don't include solids or liquids in the equilibrium expression at all. So really important. Keep solids and liquids out of the K expression. Okay, get into some fun stuff. Applications. First, application. You can determine if a reaction will move forward towards products. Move toward products or reactants. Forward towards products or reverse towards reactants. If you know the equilibrium constant and the initial concentrations. You have to do something, it's called calculating Q. Q is the reaction quotient, and this is very important. You have to know what it is. It is defined for you in that terminology sheet that you should have. And the reaction quotient looks just like K, except instead of putting in equilibrium conditions, K is equilibrium conditions, we use initial conditions for Q. Really important. So initial conditions Q, equilibrium K. All right, there's three possibilities. Q and K can be equal, Q can be bigger than K, or Q can be smaller than K. And under each of these conditions, we can say what's going to happen with equilibrium. If Q and K are equal, well, we're already at equilibrium. We're not going to shift left or right. If Q is bigger than K, you got to remember, Q and K are products over reactants. Well, if Q is too big, ultimately at equilibrium, we have to get to K. If Q is too big, the products are too big. So we got to get rid of some products, and we'll go toward the reactants. We shift to the left, because a reaction, shifting left means you are making more reactants and less products. Products are turning into reactants. However, we still say the products are whatever's on the right side. We don't, if the reaction is reversing, shifting toward reactants, we do not say that the products are now reactants. Reactants and products are defined by what you wrote when you wrote your reaction down. Okay, back to here. Third possibility, Q is less than K. And if Q is less than K, that means products are too small. Because remember, Q and K are products over reactants. If Q is less than K, Q is too small. We need to make the products bigger. Well, reactants, products. If we need to make products bigger, the reaction's going to shift to the right toward the products. Reactants go down, products go up. It's like a little teeter-totter. Okay, problem 3. We already did problems 1 and 2. This is problem 1 of this section, but it's problem 3 of today's notes. So what is problem 3? Okay. We are synthesizing ammonia. Okay, that's the same reaction we started with in the beginning. It's that reaction N2 and 3H2 makes 2NH3. This is synthesizing ammonia. You're given the equilibrium constant. And you want to predict which direction will the system shift to reach equilibrium for each of the following cases. So we're just going to plug our, remember the little 0? That means initial conditions. So we're going to plug all of our initial conditions into our equilibrium expression. But now it's called the reaction quotient, Q. And just remember, Q is NH3 squared over N2 times H2 cubed. Pause this. Calculate that out for yourselves. The answer is about to show up, so make sure you pause. Solve that out. Here's the answer. Okay. Hope you got that. Hopefully I didn't make a mistake. So, we note that this Q is much bigger than this K. Q is too big. Q is products over reactants initially. Well, if that's too big, I've got to make products smaller so that I can get to K, which means I'm going to shift, oops, this is a P, not an R. Okay, so my products were too big because my Q is too big. So that means I got to get rid of some products and shift left. Reactants go up, products go down. Okay, I already said these words in red. I'm not going to repeat them because I'm just not going to. I'm going to give you a second to read them, or you can pause. But I wrote those in red because it's a really important thing for you to know this. Products are always what you wrote on the right side. Reactants are always what you wrote on the left side. Okay. Let's do another problem. Okay. You should calculate Q. Pause. I'm going to show the answer in a moment. I want you to calculate Q and figure out if the reaction is going to go left, right, or what's going to happen. And here's the answer. Oh, no, that's not the answer yet. Here's B and C. Do C also. Do B and C. And I'm going to show the answer to both of them in a moment. So pause. You'll get the answer to both of them in a moment. Okay, make sure you pause. Do them both. See which way the reaction goes. Okay, there we go. Well, in B, that was one where Q and K are so close to 2 sig figs. They're exactly the same. They're already at equilibrium. The reaction's not shifting left or right. In C, Q is tiny. Why do I have a unit there? Ignore that unit. Sorry about that. I'll fix that in the handouts. Q is smaller than K because K was 0.0060. That was given to you in the problem. And Q is smaller than K, and the reaction shifts to the right. Okay, in addition to using our equilibrium constant to figure out which way a reaction can shift, we can also use the equilibrium constant to figure out what the final concentrations or pressures are of a chemical at equilibrium. So I've got some problems here. I don't know if you remember how to do these or not. I'm going to go through the first one, and you can follow along or pause and just do it on your own. So we have a reaction. We know that Kp is 0.133, and this is NO2 squared over N2O4, and I know N2O4. So NO2 is just going to be the square root of 0.133 times N2O4. Where is that? 2.71. Which is, changed a few things here. These were pressures. So the answer is 0.600 atmospheres. And I kept 3 sig figs because there were 3 sig figs in the numbers in the problem. And you do want to be careful about those KPs or KCs and whether you're calculating concentrations or pressures. All right, next problem. One quick thing. If you're given liters and moles, you got to make sure you calculate molarity first. You are not allowed to use moles in equilibrium constants. So you just have to make sure that you're always using molarity. So you have to do the moles over the liters. If we had a different number than 1 liter, it would change the molarity versus the moles. Okay, you may or may not remember, you actually have to set up this ICE box, initial change equilibrium. So we're going to write our reaction, PCl5 makes PCl3 and Cl2. We have our initial conditions, how much everything changes, and our equilibrium conditions, equilibrium. And then we'll also have our given or actual equilibrium concentrations if they were given to us. So we set up this chart. Okay. What do they tell us? Initially, the PCl3 is given initially right here. So we know this is 0.298 molar because it was 1 liter. What else do we know? PCl5, we know our initial PCl5, 0.00870 molar. after the system reaches equilibrium, let's see, we got Cl2 at equilibrium, the given or actual concentration, 0.00200 molar. Okay, I have enough information to solve this. So this Cl2 initially is 0. Now, first you got to figure out, is the reaction going right or left? Well, I don't have any Cl2 over here, so I automatically know this reaction has got to go to the right. There's no way it can go left if I have no Cl2. That means PCl5 is going down, PLC3 is going up, and the chlorine is going up. And in the change row, we have X and the coefficients. Okay, and X is called the extent of reaction. If there had been a coefficient in front, other than 1, in front of any of these, that coefficient would go in front of the X. So anything in front of a chemical, that's the number that goes in front of the X. In this ice box, I-C-E, ice box. Okay, equilibrium is just I plus C, initial plus change is what happens at equilibrium. So this is 0.0087 minus X, 0.298 plus X, and X. You look at the icebox and you look if an equilibrium and a given equilibrium are given, we can solve for X. So I now know X is 0.002 molar, and I can calculate now what these concentrations are here and here. So this is 0.0087 minus X, minus 0.002, which is 0.0067 molar. This is 0.298 plus 0.002, which is 0.300 molar. So I have my final concentrations, and I also need to calculate K. K is products over reactants, so 0.002 times 0.3 over 0.0067, which is, okay, so I've got my K, and I also have my equilibrium concentrations of the phosphorus trichloride and the phosphorus pentachloride. Okay, last problem. There's a little trick to this problem. You might want to try to set it up. Okay, all I did was write the reaction and my ICE and given or actual at the bottom. Sometimes this is our calculated. That last row can have all sorts of names. Calculated, given, actual. All right, we know our equilibrium constant. And we know we have 1 mole of everything in a 1 liter flask. So I know these are all 1 molar. Oh, I got to calculate Q and figure out which way this reaction's going. So Q is products over reactants. Initially, 1 times 1 over 1 times 1. That was easy. Q is just 1. K is 5. If Q is 1 and K is 5, Q is too small because it's less than K. 1 is less than 5. Q is too small. Q is products over reactants. I have to go, do you know it? You have to go to the right. You got to make more products. So reactants are going down, products are going up. I happen to have coefficients of 1 everywhere again, so it's just X. Oops, sorry, these are going up. I should have written plus X, plus X. So 1 minus X, 1 minus X, 1 plus X, 1 plus X. Oh dear, I don't know what to do. I don't have any given information, so this is different from the last one. Let's just see what I can do. I know K is CO times H2 over, CO2 times H2 over CO times H2O. Plug in my values. 1 plus X times 1 plus X over 1 minus X times 1 minus X. And that equals K. I was given K. That's 5.10. You can actually solve this, believe it or not. This is 1 plus X over 1 minus X squared, squared. That's 5.10. Take the square root of both sides, and you can solve this algebraically. I'm going to go through the whole. You try to solve this algebraically on your own. I'm going to have the solutions up in just a moment. Okay, there you have it. all figured out. It's just math. And we're done. You might want to take a second. You can pause and see if this all makes sense, but we are done for today.